Hello, and welcome back. We're moving on to section 1.2, Supervised Machine Learning, Linear Regression, Logistic Regression, and Neural Networks. So, recall from the last lecture, Supervised Machine Learning is the process of learning a function that maps input information to labeled output information. The input-output information is called the training data, and the learned function is then used to predict output labels when new input information is provided. So we're going to be coming back to this definition throughout the course, and this definition underlies this course. So let's look at some applications. First one is regression, and specifically house price prediction. So the input information would consist of features of the house, such as lot area, floor area, number of bathrooms, number of floors, size of garage, and so on. I'm sure you can think of tens of other features that might impact the price of a house. The output information would be the house price. In the case of image classification, the input information may consist of images of cats and dogs, and the output information would be the label cat and or dog for each image. In the case of bone x-rays, the input information would be the actual bone x-rays, and the output information would be normal or broken label for each x-ray. The input information may be images of animals, and the output information would be the animal name label for each image. In the case of language translation, the input information may consist of English words and phrases, and the output information may be their French translations. For a spam filter, the input information may be the messages, such as text messages or email messages, and the output information would be the label spam or not spam attached to each message. And then for auto-completion, the input information may be 2, 3, 4, or 5-word phrases, and the output information would be the next word for each of those phrases. In machine learning, as we will see, the goal is to find a function that maps the input information to the output information for the training data, and then use that function to make predictions when new input information is provided. Okay. So in this course, we're going to review and go over 3 approaches for supervised learning. The first is linear regression, and it's used for prediction of real values. It's a simple approach, which you've probably seen in your courses, and it's very useful for introducing concepts. We're next going to move on to logistic regression. It's used for binary classification. The mathematics and coding are extensions of those for linear regression. And then we're going to move on to neural networks, which are also called multi-layer perceptrons. Neural networks are used for binary and multi-class classification, and they can also be used for regression. And the mathematics and coding build on concepts for linear and logistic regression. So let's see examples of each of these 3 approaches. So first, let's start with linear regression, and we'll go to a familiar problem, line fitting. So the training data consists of the points in the plane, and specifically the input information will be the x value for each point, and the output information would be the y value. And the linear regression goal is to find a straight line that best fits the training data. A line something like this. So here we still have our training data, the points in the plane, and now we have a prediction. So once we have that prediction line, we're going to use the line to predict y values given new input x values. So why start with linear regression? It's a simple problem with a well-known solution, and this course will present a general approach that can be applied to logistic regression and neural networks. Let's move on to logistic regression, specifically the application of binary classification. So here the training data consists of input information. These are the points in the x0, x1 plane. So the actual input information are the 2 coordinates, the x0 and x1 values for each point, and the output information is a label for each point, 0 for the red points and 1 for the blue points. And the logistic regression goal is to find a function that best fits the 0 and 1 labels in the training data. In this case, you can see, roughly speaking, the 0 and 1 regions are separated by a diagonal line like this. Below that line, the labels are 0, and above the line, the labels are 1. So the goal would be to find that function. Once that function is found, we can then determine labels for new input test points, the black points in this picture. So you can see if we find that function defined by this line, then for a black point here, we would predict a label of 0. For a point up here, we would predict a label of 1. So logistic regression, the approach builds on that for linear regression. However, logistic regression is limited in the variety of functions it can represent. Specifically, it's not suitable when the boundary between the 0 and 1 regions is not a straight line. Here it's a straight line, but if we have some other boundary, then logistic regression is not suitable. So then we move on to neural networks. So again, we have an example of binary classification. And again, the input information consists of the points in the plane, the x0 and x1 coordinates for the points, and the output information is the label, 0 for the red points and 1 for the blue points. And in neural networks, the goal here would be to find a function that best fits the 0 and 1 labels in the training data. In this case, it looks like the function is roughly a parabola, and above this parabola, the label is 1, and below the parabola, the label is 0. So we can use that parabola to then make predictions. Using that function, we could then determine labels for new input test points, the black points in the picture. So a point like this, we would predict it as 0 if we found that parabola, and a point like this, we would predict it to be 1. So the neural networks, it can be used in the case of more complex boundary between the 0 and 1 regions, and it can also be used for classification with more than 2 classes. So let's look at multi-class classification now. So in the case of multi-class classification, we would have training data as shown in this picture. Here, again, the input information are points in the plane, the x0, x1 coordinates for each point, and the output information is the label, 0 for red, 1 for blue, 2 for green, and 3 for cyan. In neural networks, the goal is to find a function that best fits the 0, 1, 2, 3 labels in the training data. And you can see roughly below this parabola, the label is 0, and then we have bands where the label is 1, label is 2, and above here the label is 3. So the goal would be to find a function that fits the data in that way. So once we find that function, we use it to determine labels for the new input test points, the black points in this picture. So let's talk about the general approach for supervised machine learning that we're going to be taking. So we start with the training data, and we start with the input-output information, and then we move on to a function structure. So we're going to assume a functional form with unknown function parameters to map the training input info to the output info. We're going to define a loss function to measure how well functions map input info to output info. And then the training algorithm involves finding the function parameters to minimize the loss function for the training data. Once we have the function parameters, we can then move on to prediction. Use the function structure and learn function parameters to compute output info when new input info is provided. So I know this is a bit abstract. Let's look at it in the context of linear regression in one dimension. So the training data consists of points in the xy plane. The function structure is a line, so we assume that y equals wx plus b, where we have slope w and intercept b. These are the function parameters mentioned above. The loss function, as we will see, is a squared error over the training data, and the training algorithm, the goal is to find the w and b to make the loss function as small as possible for the training data. In the case of the prediction algorithm, we use the function structure, the line, and the learn w and b, the slope and intercept, to compute y when new input x values are provided. So this is the game plan we're going to be following throughout the course. We start with the training data. We're going to assume a functional form, the function structure, with unknown parameters. We're going to have a loss function that is used to measure how well the function maps input info to output info. Then we're going to apply a training algorithm to find the function parameters to minimize the loss function for the training data. And then once we have those function parameters, we're going to use the function structure and the learn parameters to compute output info when new input info is provided. Okay, so here's a diagram of the approach we're taking. So we start with the input, the training data, a function structure, and a loss function. We put that into the training algorithm, we turn the crank, and then we get the output. These are the function parameters, or the rules. the slope and intercept as we saw on the last slide. In the prediction phase, the input is a new input information, new x values, for example, the function structure that we have assumed, and the function parameters that we just learned in the training algorithm. We put them into the prediction algorithm, turn the crank, and then we get a prediction, the new y values, for example, for linear regression. So this is the game that we're going to be playing in this course, and we're going to go through all the math details and show how to build a framework to accomplish this. Okay, so what this course covers, the math and algorithms. We're going to go over the math and algorithms for linear regression, logistic regression, and neural networks. We're going to look at the format of the training data, the function structures, the loss functions, the training algorithms for determining the function parameters, and then prediction algorithms. Okay. And then we're also going to talk about techniques for improving performance of machine learning systems. We'll move on to the ML framework, which means machine learning framework. What is a machine learning framework? It's a machine learning framework consists of building blocks for designing, training, and validating deep neural networks through a high-level programming interface. So this course is going to present a code walkthrough / development of a basic machine learning framework in Python for setting up and training linear regression, logistic regression, neural networks using an object-oriented approach. So we're going to go through all the algorithms, and then we're going to go through and build this framework, and there are going to be videos that walk through the development of the framework and testing of the framework and using the framework to deal with lots of different machine learning problems. So we're going to have many examples in this course. And then we're going to move on to some case studies. We're going to use the framework to address 3 case studies. House price prediction, which is a regression problem. Use linear regression to predict house prices. We're then going to move on to spam classification, which is a binary classification problem, spam or not spam. And we're going to build up a neural network to classify text messages as spam or not spam. Then finally, we're going to move on to digits classification, which is a multi-class classification problem. We're going to use a neural network to identify digits 0, 1, 2, 3, all the way to 9 from images. Okay. So this gives a broad overview of what we're doing in this course, how we're doing it, and the applications that we're going to look at. So I hope this interests you and that you find it exciting and that you will continue with this course. So thanks, and we'll see you at the next lecture.